السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم. Inshallah, today we will talk about regularization, and the context was what we see here. So we were trying to optimize. First, we viewed the finding a linear model, finding good linear models as an optimization problem. What we will optimize is the error, right? So we would love to find a model that will minimize the error. So that's how we started. But then we said that the error by itself is not enough because this is the training error. So we don't want to minimize the training error to the most extent. We want to also make sure that we will not overfit. So we started to add another term here, which we called the regularizer. So we had two terms in the function that we want to minimize, the loss part and the regularization part. Last time we talked about the loss part. The problem with the 0-1 loss that we had before was that it is not smooth, and thus it is hard to optimize. So we have to approximate it, and that was the whole lecture last time. I think we spent maybe 80% of the lecture on this slide. We discussed it in detail, and I hope that it is clear why we should use one of these functions, or maybe there are also other functions, but these are just examples, as a surrogate loss function, as a substitute loss function to the 0-1 loss function. Okay? And in this lecture, we will focus on the other part, which is the regularization. Fine. Remember that the regularization part the objective of the regularization part was to avoid overfitting. And the way to avoid overfitting is to favor simple models. Okay? So try to avoid having complex models and try to find a simple model. And this idea is illustrated in this figure. If we have, let's say that we have these red points and we want to approximate a function that will pass through these points. We have infinite number of functions actually that will pass through all of these points, right? Here are two of them. You'll find the green one and the blue one, right? There's a big difference between them, of course. Which one is simple and which one is complex? The green is simple, okay? And the blue one is complex. Which one you think will generalize better? And which one you think that it's closer to the actual function that generated these points? The green one, right? The green one. So it's much simpler. Thus, we can say that simple models will generalize better. Yes, the blue function actually passed through all the points, but it's kind of overfitting here. It's doing more than what it should. Okay? The green one is much simpler, and most probably it will generalize better for the points that we didn't see yet. But both are possible solutions here, right? Both are possible solutions. And this is actually the case when we try to learn a model. We have many possible solutions. And even if we focus on linear models to fit specific data, we can fit it, or we can train a model, and we can get a model. We can get many possible models. Actually, infinite number of models. The goal of regularization is to try to avoid the models that are complex and favor more the models that are simple. Okay, with the hope that this will achieve generalization. Okay? Type. How we do that? We will have a penalty for the models that are complex. So we favor the models that are simple, and we have a penalty for the models that are complex. How is that? This is what we will see. But this is the idea. Okay? Any questions about this? So you understand now why we are doing regularization? But what will happen if we remove the regularization part? Overfitting, because complex models will be learned, okay? And that's not what we want. Okay. طيب. Now, the goal of the regularizer term is to find simple solutions. Now, let's think in terms of a linear model. What can represent a simple solution? In linear model, we have a linear combination of the features, or linear combination of the feature values, right? Each feature has a weight. So we multiply the weight for the feature times the value and sum over all the features. Type. Simple model, we can think of it that way. A simple model will only focus on small subset of the features. It will not consider all of them, or it will not consider many of them. Let's assume that we have 100 features. Do you think that a model that will focus on 10 features only and ignore the others will be simpler or more complex than a model that will consider 70 features or all the features? Which one is simpler? Okay, again, a model that will consider all the features. Okay, let's say model 1 will consider all the features. Model 2 will consider only small subset of the features. Let's say 10 instead of 100. Which one is simpler? Model 1 that will consider all, or model 2 that will consider only 10 of them? Model 2, right, that will consider only 10 of them. Okay? Probably model 2 will generalize better because it will not be distracted with so many features. It will only focus on the most important ones. Okay? Type. With this idea in mind, we might think that way. So ideally, we want most of the weights to be 0. Why is that? Because if most of the weights are zeros, that means that the corresponding features of these weights are completely ignored. Right? Why is that? We have a linear combination, right? We multiply W1 times X1 plus W2 times X2 plus W3 times X3, right? If a feature has a weight of 0, that means that it's not considered at all in the predictions. Right? Although we have values, but it will be multiplied by 0, so it will not affect predictions at all. Right? So, ignoring or not considering or not paying attention to many features, that means that we will have many 0 weights. Right? So we would like to have many 0 weights to get simpler models. Because many 0 weights means that we will have small number of non-zero weights, which means that we'll focus on small number of features instead of many. Is that clear? Right. How can we formalize this? We can formalize it that way. We can say we want to minimize the number of weights that are non-zero. Let's look at this function. This is sum over, what's d capital? D capital is the number of features. Okay, so this is sum over the features, and this is the indicator function that we saw before. The indicator function gives 1 if the condition is true, and 0 if it's not. So this condition will be true if the weight will be non-zero. So this is basically, doing it over all the features, this is basically the count of the weights that are non-zero. Right? Is that clear or not? Type. Count of the weights that are non-zero means the count of the features that will be considered. That's exactly what we want. So if we minimize that count, then we will get simpler models. Okay? Any question about this? This is one example of the ideal example of the regularizer. So now imagine that we will take this and put it back in the optimization function. The optimization function had 2 parts, if you remember. Had 2 parts, right? That's the loss, which makes sure that the error is minimized, and the regularization part, if you substitute this with the number of count, that means that if we minimize the sum of them, we will probably minimize the loss, which minimize the error, and also having less features, which means simpler models, which means we will try to avoid overfitting at the same time. So we'll get good performance plus having a simpler model. Okay? Type. Now, what's the problem with this? The problem with this is very similar to the problem of the 0-1 loss. It's not smooth. So it is really hard to optimize. So we'll not be able to really use this exact function. What do you mean by hard to optimize in this context? You heard this from me, right? Maybe not you. Hard to optimize. What do you mean by hard to optimize? Not? I don't. Soon?
Not smooth.
Smooth. Yes, it's not smooth, but that makes it hard to optimize. What do you mean by hard to optimize?
Hard to reduce the errors.
In that context, hard to optimize means it will take more time. Okay? It will be slower to optimize, which is hard. Yani hard means it will take us more time to get. Okay? Actually, there's no polynomial time to find a solution to get the minimum value for that. So we need to approximate it. Instead of using it as it is, we will approximate it. This is very similar idea to approximating the 0-1 loss function, right? That was also what we did with the loss function. If you remember from last time, we had the 0-1 loss function. It is hard to optimize, so we need a replacement for it. We need an approximation for it, okay, which was the ones that we discussed last time. Now we need something similar. Instead of this specific function that is ideal, we need a replacement. We need a function that will approximate it. Type. What do we mean by approximation here? Let's think together. The ideal function means that we will have very small number of non-zero weights, right? Right? Type. An approximated version of that is a function that will make sure that the weights themselves are small. And if we will not be able to get many of them to be zero, let's try to get many of them to be as small as possible. If we get them as small as possible, that means that maybe the effect of many of the features will be very small. Okay, so that's an approximation to our goal, right? Are you with us? Sure.
That's an approximation to our goal.
Is that clear?
Yes.
Okay. Type. So the goal now is not to get many of them to be zeros. The goal now shifted to something close, which is to get many of them to be small. So we want to encourage the weights to be small. That's the goal now. Let's see how we can do that. We will use what we call norm-based regularizers. I think you heard about L2 norm in math courses. Numerical analysis, maybe. Or maybe calculus, maybe linear algebra, if you take linear algebra. Right? That's L2 norm is the length of the vector. Right? How do we compute it? We square the values and add them and then take the square root. That's what we call L2 norm. Okay? Here, this is the L2 norm. This is the 2, that's the down here. And then we square it, just we get rid of the square root, just to make it simpler. But it's a square of the L2 norm. This is the function that is written here. Okay? So this is one possible function. Type. Why could this function be useful in our case? Let's try to understand what's going on here. what are we doing here? We are summing the square of the weights. Yani we square each weight and sum it to the other, to the next one, and so on. So all of them. Sum of the squares of the weights. If I minimize this function, remember this would be part of the optimization function, right? So now let's assume that this is the regularization function, the regularizer. Instead of the counts that we saw in the previous slide, now this is the new function. Type. If we minimize this function, will we really get small weights? Probably, right? Because we are squaring the values of the weights, and then we try to get this sum the minimum possible. When we get that sum the minimum possible, many of them will probably be very small, so that the sum of them will be small. Okay? So that's the idea here. But we can even push harder, and instead of the L2 norm, we can use L1 norm, which is the second equation here. Forget about the third one. The second equation here is what we call L1 norm. L1 norm is just the sum of the absolute values of the weights, because we care about the absolute value more than the actual value. So instead of squaring the weights, we'll just add them. Also minimizing this function will indicate that many of them will be small, right? Right? So that's also another possible regularizer. So this is called L2 norm, this is called L1 norm. And we can even go further. So LP norm is the general family of such norms, okay, where P is the power of the weight in general. So actually, if you put P equals 2, you will get L2 norm, which is the square root of this. If you put P is 1, you will get L1 norm. But actually, P can also be less than 1 in general. Okay, so P can be less than 1. Type. Let's try to understand it more and see which one is better, because now we have a family of norms, right? We have L1 norm, we have L2 norm, we have L half norm, L.25 norm, right? Because we have a family of them, right? Let's see which one will be better when we increase P or when we reduce P. So we will plot what we call contours. Forget about these two now and focus on this one. What are we doing here? We assume that we have just two features, so we have two weights only, just for simplicity. Okay? So this is weight 1, this is weight 2. And on that graph or that plot, you will see this circle indicates the L2 norm for those values, for the corresponding values of W1 and W2. So, for example, if W1 is this value and W2 this value, the norm will be 1. Actually, this circle indicates that the norm is 1. So all points on this circle have a norm of 1, but with different values of W1 and W2. So here, W1 is 1 and W2 is 0. The L2 norm is 1. Here, the opposite. The L2 is also 1. Here, maybe W1 is half and W2 is half. Or not, it will not be half exactly. It will be non-zero and less than 1. The norm is also 1. So all the points on that contour has a norm of 1. That means that you can reach the L2 norm of 1 in many different ways, right? Yani with many different values of W1 and W2, you can reach the same norm, right? Is that clear? Type. What is our goal? Our goal is to try to use a function that will favor small values of the weights. Let's look at this contour and see what is the chance with a norm of 1 to get actually small values of the weights. Let's look at this point. Do we have a small value of one of these two weights? Yes, right? W1 is 0 actually, in this case, right? Type. Getting a bit further, do we have a small value of one of the weights? So you can say that in this area, W1 is very small. In this area, W2 is very small. This area, W2 is very small. This area, W1 is very small. But in all the others, they are not small enough, right? So the chance that we get using L2 norm, the chance that we get really small weights, it's not that big. Type. Let's look at L1 norm. L1 norm will have the shape like this. Okay? When P is less than 1, I think this is when P is half. We'll have a contour like this. If we extend it further, we'll have something like this. The red one is the contour when P is 4. I think this is called cyan or something like that. Anyway, this color, this is a circle. P is 2. This is the one that we saw on the left in the previous slide. Okay? That's when P is 2. This is when P is 1. This is when P is half. You see it's sharp. This is when P is 0.25. Even sharper. Type. Now look at this one. What's the chance that using this one we will have small values of the weights? Is it higher chance than the circle and this one, or less? Higher, right? Because as you see here, all of the points on this contour has the same norm, but many of them will happen when the case that one of the weights is very small. Okay? So if we have the choice, these are all possible regularizers, okay? Possible functions to be used. If we have the choice, which one we should use? The blue one or the red one? The blue one, right? The blue one is the best. And even if you reduce P, it will be even sharper, right? So that means that when we use P to be smaller, this will favor more small values. Okay? Some of them, of course, this is in the case when we have just two weights and just to be able to see it. But when we have many weights, many of them will be small, some of them will be 0. Okay? So we can say that smaller P favors sparse weights, sparse vectors of weights. Sparse means we will have many zeros. That's in general. The word sparse, it's used with matrices. Have you heard sparse matrix? Sparse matrix means many of the enters are zeros. Okay? So smaller P favors sparse vector of weights. And I think now you understand. Right? When P increases, when P is decreased, we will get even sparser weights. Okay? Because it will favor more small or even close to 0 weights. Is that clear? So if we have the choice, then we should use the smallest possible P. So that we can get most of the enters of W to be close or equal to 0. Do you have any question about this up to this point? Type. Then the choice is clear, right? We should have very small value of P. But there is only one problem, which is that when P is less than 1, the norm is non-convex. Remember last time we said that we need the optimization function to be convex so that it will be easy to optimize. Okay? This one will be non-convex, so it will be hard to optimize when P is less than 1. When P is 1, it is convex, but it's not smooth at the axis points. If you remember here, it's not smooth. This is when P is 1. Okay, it's not smooth here. So it's a bit harder than, it's easier than when P is less than 1, but still it's not very easy. But L2 norm is convex, smooth, and thus easier to optimize. So in reality, mostly we use L1 norm. Sometimes we use also L2 norm. So those are used. Unfortunately, this one is harder, but it is the ideal. Yes?
Wasn't convex like this? Like every
Yes.
But here we get a circle and
That's, no, this is not the function, that's the contour. We are not plotting the function here. All of the points of what you see here are the same value. So it's not easy to see it here from that figure. Okay? But at least that figure can show you that this one, for example, is not smooth. Okay? Any question up to this point? Yes.
Can you explain again why it's harder for B to be less than 1?
Okay. It's not, we cannot, I cannot show it on that figure that it is non-convex because this is just the contour. It's not, I'm not here plotting the function itself. I'm plotting the points in that space where the function has the same value. But that's not the plot of the function. If we plot, actually, the function when P is less than 1, you'll find it non-convex. If you remember last time, non-convex means what? What do you mean by convex? If we take any 2 points,
everything will be underneath.
yes, the line between these 2 points will be above the function. Okay? This one doesn't satisfy this. If you plot it, it doesn't satisfy this. So it's the non-convex functions. That means that it doesn't have one global minimum, so it is harder to optimize. It's harder to find this global minimum. Okay? But L1 is easier. Still, it's not smooth at some points, but L2 is easier. Is easier than both. But L2, as you saw, there is higher chance that we will not actually get small values, but it's easier. Okay? So usually L1 is more used, I think, than L2 norm. Type. What's the big picture now? We have an optimization function that has 2 parts. The loss part, which will make sure that we will get good performance in terms of accuracy, because we will minimize that part, which means we minimize the loss, which means minimize the error. And the other part is to make sure that we avoid overfitting, is to make sure that we will get simple models. Okay? Is that clear? I hope. Okay. Right. Before we switch to the next point, you want to get back to this. That's actually what we have now, right? So we are done with this part, with the loss functions that we saw in the previous lecture, and this is the regularizer part. Now we will put both together. We'll have a loss function, and we have a regularizer. Now we optimize the sum of them. Now I want to ask you, does this function depends on the training examples or not? Now look at the function. Does it depend on the training examples? That doesn't depend on the training data that we have? Yes. Which part? Both parts or just one of them?
The test part?
The what?
What do you mean both parts?
We have 2 parts here, right? 2 factors.
The loss function depends on training data?
Yes, the loss function depends on
The training data?
the training data. How did you know that?
Because
That's the meaning of it, right? That's the meaning of it. Okay? In terms of meaning, of course, loss based on the examples, right? Loss means we have misprediction on a specific example. And you can see it even in the equation here. The loss function is function of, what's this?
predicted
The predicted value. And the predicted value, of course, depends on the examples or the feature values. طب how about the regularizer? Does it depend on the data that we have? Doesn't seem, right? Because it's just a function of the weights. In the examples that we saw, it's a function of the weights. It doesn't depend on directly. It doesn't depend directly on the data. But of course, the overall function depends on the data. طيب. If we try to minimize this function now, we will hope that this will be the minimum possible and this will be the minimum possible. Okay? So getting the minimum possible of this means as many small weights as possible, which will give us a simple model. So that will help us avoiding overfitting. And this part will make sure that we have a good performance. Okay? Type. Any question about this? What is the meaning? Are we done خلاص with the linear models? Now we know how to get the linear model? Why not? Why not? You said no, right? With high confidence also. Why? Why not? Okay. The question is, are we done with linear models? Do we know now how we can get a good linear model? Given some data. Do you know now how to get the model? What did we know up to this point?
Okay, so for this part, we only know how to choose the weights and, correct? The smaller number of weights. This part, I don't know. What's that still?
So we know now what we want to optimize, right? What we want to minimize, right? Do we know how? We don't know yet how, right? Yani I told you that, okay, we can minimize some examples of loss functions. And we can also use some examples of regularizers. And putting them together, now we have the optimization function that we want to minimize. But I didn't tell you how to minimize yet.
Oh, so we need to edit the mini tree?
We didn't talk about it yet. So that's what is missing now. What is remaining? Okay? But at least we know what to minimize. We want to minimize this. What's remaining is something very small, which is how. Of course, it's not small, but it's very important. It's the most important thing. Actually, both are important. But we need to know how to achieve this solution. Type. We'll start quickly, and of course, we will talk about that in the next lecture more. Now, how we do the optimization? You don't understand, right?
No, like, okay.
You want me to get back to the slide?
No, but Salah, we know that we need to get smaller number of weights.
Yes, we know our goal, but we don't know how to achieve it. Yani, if I told you, Salam, right? Salam, your goal is to get A in this course. Is that enough for you to get A? I didn't tell you how, right? It's exactly the same here. We want to minimize this. Shukran, thank you. Very good. I know now my goal, but I don't know yet how to achieve it.
But like, for example, for this one, like...
Let me just complete this. What do you mean by achieving the goal here? To actually minimize this function so that we can get what? What is the goal of this, of all of this? Is to find the values of the weights and the bias. That will make this whole function the minimum. So the goal is to get this function the minimum by finding possible values of the weights. Okay? So that's our target. Now we know that our target is to minimize this, but we don't know yet how. How can we get these good values of the parameters? Okay? Yes?
Isn't the thing we talked about last class, choosing the exponential function and so on, a part of the how? That's the answer to that.
No, again, similar to the example that I just gave. It's like your target is to get A. Your target is to get the minimum value of this function. But I didn't tell you exactly how you can get it. How you can get it computationally. Yani theoretically, if you plot it, manually you can do it. But we need a computational solution, right?
So the equation of finding norm 1 is not the solution.
It's not the solution. This is part of what we want to minimize. And another example. Cooking a good cake is a goal. All of us will love to have a nice cake, right? All of us know how to really have it. At least me, I don't know. Okay, thanks God that my wife can, but I don't know. I need someone to tell me how. I know their goal. I want a nice food, but I don't know how to make it. Okay, so the target, we specified the target now. The loss function and the regularizer is part of the target. Now we identified the target. Okay, for the example of getting a grade, we had many targets. You can get A, you can get B, you can get C, you can fail, right? All of these are possible targets, right? Which one is the best target? Not the best way of achieving the target.
So choosing which norm function to use was choosing which target we want. And now
Yes, exactly. Choosing the loss function, choosing the regularizer is part of identifying the target, but we didn't know yet how to achieve that target. Okay? Any question about this? Yes.
Ask about the lambda.
You insist that we don't start the new. That's fine.
About the lambda. Why do we have importance for the
Very good point. I think we discussed that before. Why do we have lambda here? What's that lambda? It's a constant.
it's
Okay.
to decide whether to give more importance to the regular.
Exactly. But do you memorize this or you understand it? What's the meaning of this? Can you explain it?
It's if we want a good performance model, or do we want a simple model? That's our-
Yes. So do you favor very simple model? If you want to get very simple model with reasonable performance, then what should be the value of lambda? High. But not so high, because if you get it so high, that means that you don't care much about the performance. Okay? And the opposite will be very small lambda will completely ignore the regularization and you just focus on the loss. Okay? Did I answer your question? Okay. Any other questions?